So now we're recording. Welcome back, everybody. Today is the last day of lecture before our test. So just as a reminder, the first test is on Tuesday of next week. So we'll be spending the entire lecture on Tuesday doing the test. And if you're in lab on Thursday, so the lab tonight, we're going to be spending the entire time just going over the review problems to help you prepare for the test. All right? And after that lab section is over, so around 10 p.m. tonight, I'm going to release the solutions to those review problems. So keep working on those as you study for the test over the weekend, and you can reference the solutions to make sure everything's going right. Okay? Any questions on that? So remember, on the day of the test, you got to bring a calculator, so don't forget to bring that, as well as your own prepared cheat sheet. So just a reminder, the cheat sheet is a half sheet of paper. You can fill it out on the front and back side with whatever you want. It's really up to you. But obviously some things that should be on there are the kinematic equations, some of the definitions of things like velocity and acceleration, and just whatever else you think might be useful for you, okay? So there's no limitations for what you put on the cheat sheet. It's up to you, okay? Any questions on that? So today we're going to wrap up the lecture on kinematics in 2 dimensions. And there's really nothing new to cover here as far as a new physics principle or a new physics equation. We really just want to see more examples, particularly of this relative velocity stuff, which can be a little bit tricky. So let's get right into another example. So we have Hector the honeybee, who always flies with a constant airspeed. So the airspeed, if you're talking about something that's flying like a plane or a bird or a bee, is the speed that they have relative to the wind, but not necessarily relative to the ground, okay? So let's say in this case the wind is blowing at 30 degrees north of east and the wind speed is 1 meter per second. So Hector sees a flower 400 meters directly north of his beehive, and he flies in a straight line from the beehive to the flower, and it takes 5 minutes to do that trip. Okay? So the question is, what was Hector's airspeed in meters per second? So we're going to start by drawing some pictures that will help us visualize the problem, and I'll show you an animation too. So hopefully you'll get a sense of what's going on, and then we'll do the calculation. So here's what's going on. The beehive is over here. This flower that the bee is trying to get to is directly north of it, 400 meters away. Okay, we're going to set up a little coordinate system that we'll use throughout this problem. It's kind of the standard way to do things where x, the positive x direction corresponds to east, and the positive y direction corresponds to north. That's what we typically do. And eventually, we're going to write down the relative velocity equation as it applies to this problem. So we're going to be using subscripts in our equation. So let me just show you what the subscripts will be. So H, that's the Hector over here. W, that's going to refer to a frame of reference moving with the wind. So just imagine a frame of reference being carried with whatever wind currents there are. That's frame W. And then frame G is the frame of reference fixed to the ground. Okay? And just like with all these problems, the velocity we measure for the B is going to be different whether we measure it relative to the ground or relative to the wind. Okay? So let's visualize the way the wind is blowing. So if we had a flag, it would sort of point along the direction that the wind is blowing in, which is 30 degrees north of east. But this vector that gives us the velocity of the wind, we want to call that VWG. So it's the velocity of the wind relative to the ground. Does that make sense why I would use this subscript notation for that? It's the velocity of the wind measured relative to the ground. Okay. Now, the thing is, since the wind is blowing in this direction, Hector doesn't want to be carried along with the wind. So he kind of has to fight the wind a bit. He has to sort of fly into it so that overall his velocity relative to the ground is just straight north. It's kind of like fighting the currents in the river. It's the same idea, right? So that's the direction the vector would have to point in to sort of fight against the wind. Make sense? And we call that vector VHW. That's Hector's velocity relative to the wind. Okay? And then this is what we see from the ground frame of reference, right? So even though he's kind of trying to go this way, we see him go straight north as seen from the ground frame of reference. Okay? So here's the equation that describes what's going on. This says, okay, VHG, that's velocity of Hector relative to ground, equals VHW, velocity of Hector relative to the wind, plus VWG, velocity of wind relative to ground. And I know that I set this up right because the H subscript appears on the left, the G subscript appears on the right on both sides of the equation, and the W subscript is on the inside. So that's just a quick check to make sure it's in the right form, okay? So we could go about doing this a number of different ways, but I think the best way to do this is to start with a diagram. So in this equation, there's some vector addition going on, right? We're adding these two vectors, and then as a result, we're getting this vector. So let me just ask you real quick. Velocity of the wind relative to the ground. That's pointing in the first quadrant like that, okay? Velocity of Hector relative to the ground. What direction is this one pointing in? So just straight north, right? Because relative to the ground, we just see it move straight north. So this one's straight north. And then this one, as we said, is kind of like in the second quadrant like that. So you see how the vectors would add? Let's do it real quick. This is VHW. So he's kind of pointing into the second quadrant like this. Added to VWG, that's the wind velocity going into the first quadrant like this. And then you see how the resultant is straight north. That's the whole point. We get a resultant velocity that's straight north. Okay, so are we clear on the setup here? So what do we want to solve for? We're trying to solve for Hector's airspeed. So that's Hector's velocity relative to the wind right here. So in this equation, the vector I'm interested in is this one right here. Make sense? All right, so let's go through it. I think that's the setup. Yeah, so in order to find the airspeed, we're solving for this vector. And since it's just a speed, we're taking the magnitude of it, okay? That's the idea. All right, so now we're going to solve this. Any questions before we do that? All right, so I'll start by copying down the equation, which is I think this pen is out of ink. Hold on a second. Okay, so the equation that we had on the slide was VHG equals VHW plus VWG. So hopefully you understand what these vectors mean now, okay? The one we're trying to solve for is, again, this one, VHW. So the simplest thing I could do is just rearrange the equation by subtracting this vector from both sides. So I have VHW equals VHG minus VWG. Okay, just a simple rearrangement. Okay, so now let's do a little bit of work. If I knew exactly what these two vectors were, I could just plug them straight in, do the vector subtraction, and then I'd basically have my answer, right? But let's really focus on how that's gonna work out. So let's write down some information we have. The wind is blowing at 1 meter per second. And the direction is 30 degrees north of east. Okay? So let's think about how I could write that vector in terms of components. Because if I'm subtracting two vectors or adding two vectors, I want to have each one in XY form, as you remember, right? So the velocity of the wind relative to the ground, here's how I would do that. I'm going to take 1 meter per second. That's the magnitude. But if I take cosine of 30 degrees, That's the x component, right? So I'll put a little I hat next to that. And then if I take 1 meter per second times sine of 30 degrees, that's the y component. So cosine 30 degrees, you may remember what this is from the unit circle. Or you can just punch it into your calculator. What's 1 times cosine 30? It's root 3 over 2. Does that look familiar to anyone? Cosine 30 is root 3 over 2 meters per second times I hat. Anyone remember what sine of 30 degrees is? Because we're just multiplying that by 1. It's just a half, right? So this is how we take the wind velocity and break it into x and y components, all right? Okay, now, let's think about, so basically here, I'll put a check mark right there. We dealt with VWG. Let's think about how to deal with VHG, okay? That's Hector's velocity relative to the ground. And remember, this one is pointing straight north, okay? So let's write down the information we have. Hector takes 5 minutes to travel 400 meters. That's the distance. Due north is the direction. All right? So if someone moves 400 meters due north and it takes 5 minutes, here's how I can write the velocity. So remember, we're calling this velocity VHG, so just put that out there. If I'm traveling due north, what is the x component for my velocity? Remember, we're thinking x is east, y is north. So what would the x component for this velocity be? 0. Yeah, it'd be 0, right? There is no east-west velocity going on at all, so the x component is just 0. Then for the y component, well, I'll just use these numbers. The fact that we've traveled 400 meters in 5 minutes. What's 5 minutes if I express that in seconds?
3,000.
It's 300. Yeah, because it's multiplied by 60, right? So I could say this is 400 meters over 300 seconds, j hat, which is just 4/3, right? That would simplify this to 4/3. All right, so then we can crunch the numbers. We have VHW equals VHG, which I'm going to copy down here, 0 I hat, and then we have 4/3 of a meter per second j hat, and then I want to subtract off this vector, which I wrote out over here. So I'm subtracting off this thing, root 3 over 2 meters per second I hat plus a half of a meter per second j hat. Now, by the way, if you prefer, you can write this all in decimal form, but I'm just writing it as fractions. Okay, so what do we have? So for Hector's velocity relative to the wind, I have 0 minus root 3 over 2, so that's just minus root 3 over 2 meters per second I hat. So that's the x component. For the y component, I have 4/3 minus 1/2. You see that? Just subtract the components down the list. 4/3 minus a half. That simplifies to 5/6 as a fraction. Okay? So those would be the components of Hector's velocity relative to the wind. So the last thing we would do is take the magnitude of that. Because that would be Hector's speed relative to the wind, which tells us basically how fast is he capable of flying. We want to know that. This is minus root 3 over 2 meters per second, square that, plus 5/6 of a meter per second, square that, and then take the whole thing under the radical. This comes out to about 1.2 meters per second if you work it out. Okay? So that's that problem. Any questions on how this works? Okay. We'll do a few more examples and hopefully it starts to click. Okay, so let's do another one. This is probably something you've experienced if you just kind of notice what's going on around you when you're driving in a rainstorm or a snowstorm, for that matter. But imagine that during a rainstorm, the raindrops are falling straight down with a speed of 15 meters per second. And of course, when we say that, we mean relative to the ground, the raindrops are coming down at 15 meters per second. So let's say that you're not just standing still on the ground, but you're driving. And you're driving on a flat and level road, so you're not going up a hill or down a hill or anything like that. And your speed is just a constant 25 meters per second. Again, when we say that, we're implicitly measuring that relative to the ground. Okay, so here's the question. From your perspective, at what angle are the raindrops coming in? See, if you're just standing still on the ground, well, you'd say they're just moving straight down, right? But if you notice what this looks like when you're driving, it's almost like the raindrops are coming in at some sort of angle towards your windshield, right? We're trying to figure out what that angle is, okay? So you're all familiar with what I'm talking about? Okay. So let's go through it. How are we going to deal with this? So what I'm going to do is draw a picture of what's going on. And in order to do that, we're going to have a coordinate system set up. So the y direction in this case is going to be up. And then the x direction is just whatever the horizontal direction is. Doesn't really matter. Okay? And what we have here are, so let's say that I'm going to draw a picture of what's going on in the ground frame. So I'm going to show you what all these different motions look like from the ground frame of reference. Okay, so if we see a raindrop in this frame of reference, I'm just seeing it move straight down. And if I take a look at the car as it's going by, I'm seeing it move in the horizontal direction, right? So let's label these velocities. So because both of these velocities are relative to the ground, I could call this one VRG. It's the velocity of the raindrops relative to the ground. And then I could call this one VCG. It's the velocity of the car relative to the ground. Okay? And just to be clear, R is the rain, C is the car, of course, and then G is the ground. So that's the key to this notation. Okay? So what would I say for VCG? Tell me what that is as a vector in x and y component form. So something I hat plus something j hat for this guy. Yeah, it's just 25 meters per second I hat, and that's it. There's no y component, so just leave it at that. Okay, for VRG, what should I say about that?
15 meters per second j hat?
But I put a negative sign on that because we're moving downwards. But yeah, so negative 15 meters per second j hat. Is that clear? The velocity I want is the velocity of the raindrops relative to the car. I know that from the perspective of the ground, the velocity is straight down, but relative to the car, that's what I care about, okay? So the relative velocity equation does exactly this. It takes a velocity measured in one frame of reference and it converts it to a velocity in a different frame of reference, okay? That's the whole thing. So let's try this out. Let's try setting up the equation. I mean, the simplest thing to do is just say, look, this is the velocity I want. So I'm just going to put that on the left side of the equation. And that automatically tells me what needs to go on this side, where I'm adding two velocities together, right? Because the order of subscripts is, I want the R to appear on the left side, and then I want the G to appear on the right side like this. Or sorry, C, because, yeah, that's a C right there. And then I want the G to appear on the inside like this. Yeah, that's what I meant to say. Okay? So we clear on that's just how we set this equation up? Okay. But check this out. VRG. We know what that is. That's this vector right here. This one says VGC. We don't have that one. So to put this in words, this is the velocity of the ground relative to the car, right? What we have is the velocity of the car relative to the ground. Do you guys remember how we switch between these two? Like if I just flip the subscripts around, how does that work? Yeah, I can just write this as VRG minus VCG. So if I flip the subscripts around, that just introduces a negative sign. That was the last thing we talked about on Tuesday. All right, so now let's just put the numbers in, okay? We've got VRG at minus 15 meters per second J hat, that's this guy. And then we're subtracting VCG, which is 25 meters per second I hat, okay? So in other words, does it make sense that this vector would be in the third quadrant with both a negative x and a negative y component? Because this is how you're seeing the raindrops come in. Relative to your car, that's what you're seeing, okay? And let's actually just take this vector and label its components, right? This is the y component right here. This is the minus 15 meters per second. This is the x component. That's minus 25 meters per second. So that from your perspective in the car, this is how you see the raindrops moving. What direction do you see them moving in? That's some kind of angle. Okay, so remember, the way the problem is worded, we want the angle off the horizontal. So this line is the horizontal. So this angle relative to the horizontal, let's call it like alpha or something like that. Any ideas how I can solve for alpha? Yeah, just use tangent. Try it out. Tangent of alpha equals what exactly? What's the definition of tangent? Let's just go through that again. Yeah, so it's opposite over adjacent. The opposite side is minus 15 meters per second. The adjacent side is minus 25. So to solve for alpha, I'm going to take the inverse tangent of 15 over 25. Can someone crunch those numbers? Inverse tangent of 15 over 25?
30.96.
Yeah, so 30.96 degrees, which rounds off to, we want to keep 2 sig figs on this, so about 31 degrees below the horizontal. So in the car, we see the raindrops coming in at this angle, 31 degrees below the horizontal. Okay, any questions on how this example works? No? All right, we're going to keep moving then. So the next one is a little bit challenging. There's one on the study guide kind of like this. So here's what's going on. We're combining two of the big ideas from this lecture, which are relative velocity and projectile motion. So in other words, we're going to throw a projectile from a moving car in this problem. So here's what's going on. In the latest Indiana Jones film, Indy throws a bomb from his car into an enemy's car. Both of these cars are moving on a straight section of road at a constant speed. So Indy's car is moving at 23.1 meters per second, and the enemy's car is moving at 32.3 meters per second, both relative to the ground. Okay, the enemy's car is 17.0 meters in front of Indy's car at the moment when he throws the bomb. So Indy's like behind him, he has to throw the bomb forward to get it into the enemy's car. Let's say that Indy throws the bomb so that its initial velocity is at 45 degrees above the horizontal. Okay, so that's the angle we're going to throw this at, 45 degrees above the horizontal. So what is the initial speed that he has to throw it at such that the bomb lands in the car? Okay, it's kind of complicated, so we're going to break it down and we're going to show some animations. Okay, so here's the situation. Let's draw a picture. So first of all, I'm going to use these subscripts at various times in the problem, okay? So when you see G, that is the ground frame of reference. So like some velocity that a car has or the bomb has, that's going to be what we use to say it's relative to the ground. Okay, I, that's going to be Indy's frame of reference. So that's going to be a frame of reference moving with his car. And then E is the enemy, B is the bomb. Those are the two objects that we're keeping track of the motion of, okay? All right, so let me show you an animation of what's going on as we see it in the ground frame of reference, okay? So I'm just standing on the side of the road and I'm watching this happen. I'm gonna see Indy's car moving forward and the enemy's car moving forward, both at some constant speed, okay? That's what happens. So when the enemy is 17 meters ahead of Indy, that's when the bomb is thrown. And the point is we want it to land in the car, okay? So there's an unknown that's being brought into this. If we say that the bomb is thrown at t equals 0, then there's some time where it lands in the car. And we don't know that, so that's going to be something unknown in our equation. So we'll call that t final for the time that it lands in the car, okay? Now I just want to see where you guys are at. Do you remember problems like this that we've seen before, where one object either meets another object or collides with another object? What do we do in that situation? So we set what exactly equal to each other? Position, right? If the bomb lands in the car, then at this time t final, it has to be at the same position as the enemy's car. We need that to happen in order for this to work out, right? So that's all well and good. But let's take a look at the same situation in a different frame of reference, okay? So this is the picture of what it looks like relative to the ground. I'll show you one more time. Let's now look at the same animation, but from Indy's perspective. So from the frame of reference that's just attached to his car, okay? All right, so let's take a look at what that looks like. So, sorry, let me just show you the animation, then I'll explain the equations in a second. So in Indy's frame of reference, he would say, I'm not moving, and this car is just moving ahead of me at some speed. And this is what it would look like. Let me show you one more time with the animation. Does that make sense, what I'm showing you? Let me know if it's not making sense. Okay. So let's explain some of these equations then. So we're gonna work in this frame of reference to do the problem. Okay. So first of all, let's take a look at this second line. This says VEI. What does that mean? It's the velocity of the enemy's car relative to Indy. Relative to the ground, the enemy's car is moving at 32.2 meters per second. But relative to Indy, you have to subtract off his velocity, which is 23.1 meters per second. Okay? And if you do that, 32.2 minus 23.1, you get 9.1 meters per second. Okay, so Indy sees this car ahead of him gaining an extra 9.1 meters every second. Does that make sense what I just said here? So that's what Indy sees for the velocity of the enemy's car. Okay, Now the bomb, let's get to that over here. We're told that the bomb is going to be thrown at an angle of 45 degrees relative to the horizontal. So if we show the initial velocity as a vector, it looks something like this, right? Where it's pointing at 45 degrees relative to the horizontal. So what I can do is I can take that and I can break it into components, right? I can write the x component for the bomb's initial velocity, and I can write the y component, okay? But here's the thing. We do not know what the speed is to start off. We don't know how fast he's throwing the bomb. That's what I'll call v naught, just the initial speed. But if I wanted to write what the x component is, I would just say v naught cosine 45 degrees, okay? And for the y component, I would say v naught sine 45 degrees. So v naught is another unknown in addition to t final. So we have these two different unknown quantities. Does that make sense? Yeah? No? Okay. All right, so remember we said, one of you came up with this already, that at the moment when the bomb lands in the enemy's car, the positions are equal, okay? But we're now dealing with two-dimensional motion, right? So not only are the x positions equal, but so are the y positions. You get that? So it's x and y both have to be equal to each other. So let's think about this. XE equals XB. The x position of the enemy equals the x position of the bomb. YE equals YB. The y position of the enemy equals the y position of the bomb. Both have to be true, right? If it's just the x positions equal, but not the y positions, it doesn't work. You don't land in the car, okay? They both have to be equal. So here's what we're going to do. We have a sort of general kinematic equation for position when we're dealing with 2D motion, which is this: r equals r naught plus v naught t plus a half at squared. We're going to apply that to the enemy and the bomb, and we're going to write x and y components for the enemy and the bomb. So let's get to doing that. Okay, so the bomb is a projectile. We're going to use projectile motion equations to describe how it's moving through the air. Okay? So let me just remind you how this works. For a projectile, we take the initial x position, which for the bomb is 0, because we set the origin of our coordinate system right where India is. The initial x velocity, we said earlier, is v naught cosine 45 degrees. That's multiplied by t. And then for a projectile, remember, we don't accelerate in the x direction. Okay, so I just set the acceleration part to 0. What about for the y position? Well, again, we say the initial y position is 0 because in the coordinate system we set up, the bomb starts at the origin. And then we have v naught sine of 45 degrees as the initial y velocity. That multiplies t. And then remember, acceleration is just minus 9.8 meters per second squared. So I'm just going to put that right in here, okay? So it's at minus 1/2 times 9.8 meters per second squared, t squared. Those are the equations that describe how the bomb is moving as seen from Indy's perspective, okay? So just applying the projectile motion equations. Okay, for the enemy's car, now we want to write down the x and y position of the enemy's car, okay, in the same kind of way. So for the enemy's car, remember, that's just moving in the x direction at a constant velocity. So there's no acceleration happening, it's just constant velocity. And there's only motion in the x direction. There's no motion in the y direction for the car. Okay? So here's what we have. For the enemy, the x position, let's think about it. The initial position is 17 meters, because we were saying the enemy starts off 17 meters ahead of where Indy's car is. 17 meters goes in for that. And then, as we worked out, Indy is seeing the enemy's car moving ahead at 9.1 meters per second. So that's what we put in for the velocity here, and that multiplies the time. But again, there's no acceleration. Everyone's just moving at a constant speed, so we don't put in anything for that. And for the Y position of the enemy, that's just real simple. The initial Y position is 0. The enemy is not moving in the Y direction, so there's no Y velocity. So this is 0 also, and there's no Y acceleration. So the enemy just stays at Y equals 0 the whole time. That's just what this is saying. Okay? All right, so let me know if you have any questions about how we're setting this up, because the rest is just some math. Okay? So let's get into that math then. So remember, I have the Y position for the enemy, I have the Y position for the bomb. They have to be equal. So let's equate them. The Y position for the enemy, we said was just 0. The Y position for the bomb was this expression. Okay? And notice I'm going to, instead of calling it T, I'm going to just call it T final, because that's the moment the bomb lands in the car. Okay, so we have 0 equals V naught sine 45 degrees T final minus 9.8 T final squared. So notice that we can't directly solve for either of these. So we have two unknown variables, right? So what we're going to have to do is maybe try to sub one of them out. Let's try that. Let's try subbing one of the variables out. So notice I have T final as a common factor. I can pull it out, and what I get is T final on the outside multiplied by V naught sine 45, and then minus a half times 9.8 T final. So this is squared initially, but I'm basically separating out the two factors of T final like this, okay? So basically, just divide out this T final, get rid of it, and now we're left with 0 equals the thing in the brackets here, okay? And if you rearrange that, here's what you'll get, okay? So if you take this formula that's shown here, and you just solve for T final, you'll get this. 2 times V naught sine 45 degrees over 9.8 meters per second squared. Okay, so that's T final, but since we don't know what V naught is, it's going to have to look symbolic like this. Okay. So the other thing we do is just try to crunch some of these numbers, right? So I have 2 times sine 45 over 9.8. I don't want to keep writing that over and over again. So if you just calculate what that is, it comes out to 0.144. Okay. So 0.144 is multiplying V naught. And if you work out the units, it's actually seconds squared over meters. Okay. So this is something we have for T final. We could plug it into another equation later, but let's just leave it at that for now. Okay. So the next thing we do is we equate the X positions of the enemy and the bomb. And we just use what we came up with before for that. So remember, this is what we had for the X position of the bomb right here. And this is what we had for the X position of the enemy. So we're setting these two equal to each other. So we have V naught cos 45, T final, equals 17 meters plus 9.1 times T final. We're trying to solve for V naught, okay? If you're getting lost in the math, the point is we want to solve for this V naught thing, okay? So one way to do that is to take the T final expression that we worked out up here and then plug it in here and here. And then when you do that, the only unknown variable is V naught, okay? So it's going to look a little messy, but I'm going to do that substitution. See how it's the same equation, but for T final, I just plugged in this expression up here. So I did it where it appears there and where it appears there, okay? So I don't want to spend too much time just going through the algebra. It's a bit of a grind. But if you simplify this, here's what you'll get. basically, you see how I have V naught times V naught in this term right here? That's V naught squared. You see how I just have one factor of V naught over here, and then I have a constant term? That's a quadratic, because I have a V naught squared, I have a V naught term, and then a constant term. It's a quadratic, and this is what it looks like when you just clean everything up, okay? So we get 0.102 V naught squared minus 1.31 V naught minus 17 equals 0, okay? That's just what this expression works out to when you crunch some of the numbers. And what's the quadratic formula? Remind me again.
Minus V plus minus square root of E squared minus 4AC over 2A.
Very good. So yeah, that's the formula we'd have to apply to solve for V naught here, right? So someone tell me, I have A, B, and C in the quadratic formula. Which term is A in this case?
0.102.
That's the A term, right? Because it's multiplying V naught squared. What's the B term?
Negative 1.31.
This is my B term, and then this would be my C term, right? So just plug all that into the quadratic formula, A, B, and C. Remembering that to solve it, we have minus B plus or minus square root B squared minus 4AC over 2A. You're definitely going to use this formula on the test, so remember it, okay? And here's what you get. You get a negative answer, minus 8 meters per second, and you get a positive answer, 20.8 meters per second. And this is the correct one, the positive solution, okay? So that's it. Indy has to throw the bomb at 20.8 meters per second in order for it to land in the enemy's car, okay? So there's a lot going on there, but hopefully you see the steps. The math gets a little messy, admittedly. Any questions? Okay. So that's the sort of official end of the lecture, but let's do some more practice problems. Okay, the test is coming up. Let's do a few examples dealing with relative motion and with projectile motion. I think those are some of the more challenging topics that we've seen, right? So let's get into it. Let's try this one. So you are attempting to use a homemade cannon to launch a potato onto the roof of a 45-meter tall office building. You set up the cannon at ground level, 75 meters away from the base of the building. At t equals 0, you launch the potato with an initial speed of 48 meters per second at an angle of 55 degrees above the horizontal. So 2 questions. Question 1. At what time does the potato land on the roof? So how long does it fly through the air until it lands on the roof? And then secondly, how far onto the roof does the potato actually go? So if you've been working on the review packet, you may notice there's a problem a lot like this on the review. But let's see how it works out. So let me ask you this, because I want to sort of test your intuition, okay? Sometimes when we want to know how far a projectile has traveled, we'll use the range equation, right? Am I able to use the range equation in this example?
No.
What's the reason for that?
It has to start and stop on the same level.
Yeah, so if you're tempted to just go to the range equation here, because that would be simple if we could do it, but it's just not valid here. The range equation only works if you start and end at the same height. And that's not the case, right? We start at the ground and we end up on the top of the building, so it's not going to work, okay? So instead, we have to go back to the basics. Let's just draw a picture of what's going on here. We have our standard coordinate system for projectile motion with the y-axis pointing up, the x-axis pointing horizontally. And let's just have the projectile start off right at the origin. So the office building, let's put it over here somewhere, and let's just sketch out the trajectory of the projectile. Something like that, right? It's shot from ground level goes up, comes back down, and then it lands on the roof. So to be clear, what we're trying to find, well, is the time that this happens. We don't know. But also the distance, in particular this distance right here. How far onto the roof did the projectile go? Okay? Now I'll point out that there's another distance that's relevant here. So the distance between the starting point and the base of the office building right here, that's 75 meters. And then the height of the building, which I'll point out right here, is 45 meters. Okay? So we're going to do a little bit of work to just set the stage. All right, so if this is my starting point, and this is my ending point, what can I say about my initial position? X naught, Y naught. What is my initial position here? Yeah, so I set up the coordinate system so that we're at the origin to start. So that means X naught, Y naught is just 0, 0. Okay? Now, what can I say about the final position, which is X comma Y?
Y is 45 meters.
Okay, so the Y coordinate is definitely 45 meters. We'd agree that the projectile is 45 meters off the ground at the moment it lands on the building. Can we say anything about the X coordinate? So we can't actually say 75. If we did that, we would be assuming that it just barely makes it onto the roof.
X plus 75.
Yeah, so here's the thing. X is just not known. The best way to say this is we don't know how far in the X direction the projectile has traveled, at least not right off the bat, right? So we don't want to make any assumptions about what that distance is. Okay. What about the initial velocity? This is another thing that's going to come in our equations. We're going to have v naught x and v naught y. So do you remember how to do this? How do I calculate the x component of the initial velocity of the projectile?
Initial velocity times cosine of the theta.
Yeah, so I take the initial speed at the time of launch times cosine of the angle that we launch it at. And in this case, we know both of these things, right? We know that we launch at a speed of 38 meters per second, and we launch at an angle of 55 degrees. So that would be v naught x, okay? And then for v naught y, what would I say about that?
Same thing, but you're using sine.
Yep, same thing, but with sine. So v naught sine theta naught, that's 38 meters per second, sine of 55 degrees. Okay, I think we've pretty much set the stage, right? This is all the information we know. So, how do I proceed? Any ideas? Let's say we want to solve for the time first, just to give us a roadmap. Let's say I want to solve for t first, and then later I'll solve for x, how far we've traveled horizontally. So if I'm trying to solve for t, how should I do that? What equation is relevant?
You can use
Yeah, I should use my y position equation for a projectile, which is y equals y naught plus, what's the next term in this equation? V naught y, that's the initial y velocity, and then times time, and then what's the last thing here? Okay, so we all remember this? This is the equation that describes how the y position of the projectile changes over time.
Can we also use the final velocity equals initial velocity minus gravity minus acceleration?
Yeah, so we could, but then we don't know what the final velocity is the thing. So we could use that if we, another way found what final velocity was,
Okay.
but that would mean we have to sort of use two equations together. So it's not, that's not wrong, you could do that.
But we're not assuming that final velocity is 0.
Okay, good question about that, right? Oh, yeah, so of course, you know, if the potato just splatters on the roof, then its final velocity is 0, right? But this equation, or any equation for projectile motion, is only valid when it's flying through the air. So when we talk about its final velocity, we really mean like just before impact, okay?
Okay.
That's really what it means, because as soon as we hit the ground, projectile motion equations don't apply anymore. All right, and we'll see later how to deal with that when we get to Newton's laws of motion and stuff like that. But the equations we're using are only valid when you're moving through the air, not upon impact or anything like that. Okay?
Sure.
So, all right, if we're going to go this route, tell me each variable what the value is. Okay, so y, what do I put in there?
45.
That's 45 meters, because that's our final y position. Why not? What do I put in there?
0.
0. Okay, v naught y, well, we already wrote that down. That's going to be 38 meters per second, sine of 55 degrees, right? That's multiplying t. And then I have minus 1/2 g, which is, what's the value of g? 9.8 meters per second squared, t squared. Okay, so it looks like this is a quadratic. That's generally going to be the case. If you know the launch height and you know the landing height of some projectile, to find the time that it's in the air is generally going to involve some kind of quadratic like this. Okay? So let's write this in a nicer way so that we can apply the quadratic formula. Remember, with the quadratic formula, we want it to say 0 equals something, right? So I'm going to just subtract 45 meters from both sides to write it in the standard form, okay? So I have 1/2 times 9.8. I should say minus 1/2 times 9.8, which is minus 4.9 meters per second squared, t squared. Can someone do this real quick? 38 times sine of 55, what is that?
31.1.
31.1, so this is plus 31.1 meters per second times t. And then remember, I subtracted the 45, so then I have minus 45 meters on this side. So my A term is this, my B term, and my C term are shown here, okay? So I want someone out there to apply the quadratic formula, okay? We're going to do T equals minus B plus or minus square root B squared minus 4AC over 2A. So I know what I'm plugging in for A, B, and C. It's shown right here, okay? Someone tell me what we get. We get two solutions, right? Because one, you apply the positive sign. The other, you apply the negative sign.
2.23 seconds and 4.12 seconds.
Okay, so 2.23 seconds, that's one of them, that's correct. And yeah, the other is like 4.12 seconds. Let's keep track of our sig figs here. Okay, now which one of these do I want to pick? They can't both be right. Right, I either land on the roof after about 2 seconds or maybe it's about 4 seconds. Which one is correct?
4.12.
So we want to pick this one. How do you know that? That's right, but how do we know?
Because it comes after the second half of the arc.
Yeah, so here, let's really think about what we did. We basically used our kinematic equations to ask the question, at what time do we reach a height above the ground of 45 meters? We do that twice, right? Once is on the way up, somewhere over here, right? And then we actually overshoot that, and then we come back down. And then we reach that height again at a later time. So it's obviously the larger time where we actually are on the way down and landing on the roof. Okay, not the smaller time. That's how we know. Okay, so we've solved for the time. Now, how can I calculate how far onto the roof we've made it? What equation can I pull out for that? Yeah, what equation to solve for horizontal distance traveled, basically?
Solving for x.
Yeah, so here, let's just directly solve for x. X means final x position, right? So distance from here to here. So what's our kinematic equation? X equals x naught
V naught xt.
plus v naught xt, and there's no acceleration, so there's nothing else to write. There's no acceleration in the x direction, okay? And then we can plug in what we know. X naught, what was that equal to? 0. And then v naught x, that was 38 meters per second times cosine of 55 degrees. And then t is 4.12 seconds. So what is that equal to?
89.79.
Yeah, so like 89.8-ish, right, meters? Keeping 2 sig fixed. Okay, now, that's not quite the answer, but the answer we want is just around the corner. I'm trying to solve for this distance d, right? That's not the total distance the projectile has traveled. It's the total distance minus 75 meters, right? So d is the distance we found, 89.8 meters minus 75 meters. So that's just how far onto the roof we go, not how far total do we go. And was that
14.
14.8? But we'll round that to a nice 15 meters. Okay, so we make it about 15 meters onto the roof this way. Any questions on this one? Okay, let's keep going. I think we have time for another one. Yeah, let's do one involving relative velocity, because I think this is something we could practice more with. All right, so kind of similar to the one we did with the honeybee, except now we have an airplane. So the wind is blowing at 50 miles per hour in a direction 30 degrees north of east. The pilot is flying a plane with an airspeed of 400 miles per hour. So when we say airspeed, that is the speed of the plane relative to the wind, but not necessarily relative to the ground. Okay, what direction does the pilot need to point the nose of the aircraft in order to go due north relative to the ground? Okay, let's just kind of vaguely picture this. 30 degrees north of east. So if this is east, go 30 degrees north from there, and this is our wind velocity. So the plane has to fly into the wind a little bit. The plane has to have its nose aiming into the wind a little bit, so that relative to the ground, we just move straight north. Okay, so it's like we're fighting the wind. Okay, so we'll get the angle for that. Like, what direction do we have to point the nose of the aircraft? And then, as a follow-up, what is the speed of the plane relative to the ground that results? Okay, so let's work this one out. Okay, so we have P, that's the plane, and that's the object in question. G is the ground, frame of reference. And then I'll call W the frame of reference moving with the wind. Okay? So that just defines our subscripts. So right away, we can just write down the relative velocity equation. What we want to know at the end of this is what is the velocity of the plane relative to the ground? That's the last question we have. So let's write down the relative velocity equation with this on the left side. That means on the right side, I'm going to have two things added together, where subscript P is going to go here on the left, and then subscript G is going to go here on the right, and then subscript W is going to go on the inside, okay? So that's just how the equation gets set up. So let me ask you a few questions about these different vectors, okay? So we're going to use a coordinate system as we go, where x is east, y is north like this. It's the standard thing to do. Okay, so for this velocity vector, velocity of the plane relative to the ground, can you just tell me what direction that's pointing in?
East.
Okay, velocity of the plane relative to the ground, that's just due north. So it's exactly north. Because relative to the ground, we want to travel north. I mean, try to imagine this in a practical scenario, right? Maybe I'm flying the plane to a city that's exactly north of here, right? So relative to the ground, I want to be moving north. Okay. What about this one, the velocity of the wind relative to the ground? We don't have to say anything too specific. Let's say, like, what quadrant is that one going to be in?
First.
Yeah, the wind relative to the ground is like this, 30 degrees north of east. So that's in quadrant 1. So what would this vector have to be to get this to work out? What quadrant would this one have to be pointing in? Yeah, it'd have to be pointing in the second quadrant. Let me show you how that works real quick, okay? All right, so the velocity of the plane relative to the wind. I'm claiming it has to point in the second quadrant like this, such that when we add the velocity of the wind relative to the ground, we add this vector, we get something that's pointing straight north, which is what we want, okay? So we have velocity of the wind relative to the ground, and then we have our resultant velocity, the velocity of the plane relative to the ground, okay? So the first question is actually asking us, how is this vector angled? Right? We can see it's pointing somewhere, but at what angle is it pointing? That's the first question we'll answer, okay? And then the second question is for this guy, like how fast is the plane moving relative to the ground? So what's the magnitude of this one, okay? All right, let's make a few other marks on this. If the velocity of the wind relative to the ground is 30 degrees north of east, okay, that's the angle right there. That's the 30-degree angle, okay? So what I'm going to do is I'm going to label the angle that we do not know for this vector, and I'm going to measure it off the x-axis like this. You see that? So I'll just call whatever that angle is theta, and we'll work it out. Okay? So here's what we're going to do. The relative velocity equation that I just wrote down, I can break that into two separate equations, actually. One for the x motion and one for the y motion. I'm always free to do that if I have a vector equation like this, okay? So let's write down the x equation. Okay. That says, I'm going to actually explicitly write this out. VPG in the x direction equals VPW in the x direction plus VWG in the x direction. So I'm just picking out the x component of each part of this. Okay, for the plane, for its velocity relative to the ground, what is the x component? So this is the vector that's pointing straight north.
We don't know this. We didn't.
We know it's 0, right? Because if we're pointing due north, this vector has no x component, okay? Okay, velocity of the plane relative to the wind in the x direction. Well, with any vector, if I take the magnitude times cosine of the angle, that should give me the x component, right? So the magnitude of this vector is 400 miles per hour. Okay? Because that's how fast the plane moves relative to the wind. But if I take cosine of the angle theta, then I'm picking out the x component of that vector. Okay? Is that clear? And then for the velocity of the wind relative to the ground, well, that is 50 miles per hour. And if I take cosine of the angle for that vector, which I actually know is 30 degrees, then I'll get that x component, okay? So are we cool with how this equation was set up? All right. So I'm trying to solve for theta. So let's throw this term to that side, so it's negative. And then let's divide out the 400 miles per hour. So again, cosine theta equals minus 50 miles per hour times cosine 30 degrees, and then divide out 400 miles per hour. All right? If you crunch these numbers, you're going to get minus 0.1083. So you can verify that. And of course, if I just want theta, I'll take the inverse cosine on both sides. So try this for yourself. Inverse cosine of minus 0.1083. It's going to give you some angle. And tell me what the angle is when you do this.
96.2.
Yeah, it's 96.22 degrees. I should be keeping track of my sig figs. We're rounding up to 3 at each step. So let's think about that. This is saying if we're looking at our plane's velocity vector relative to the wind, I would measure it like this. I'd start here, and I'd go 96.22 degrees this way. And then I'd be pointing in the correct direction. Okay? So I could write it that way, or I could say this. I could say it's 6.2 degrees west of north. So if I'm pointing north, and then I just go 6.2 degrees this way, then I'm at my angle. I'm in the direction I want to be going in. Okay? So either way you express this is fine. Do you have any questions on how we got that? So actually, we only have looked at the x equation so far. So there's a y equation as well. And that's going to help us finish the problem and just get the last part of this. So remember, we want to know how fast the plane moves relative to the ground. We know that relative to the wind, it moves at 400 miles per hour. But relative to the ground, that can vary depending on how the wind is blowing, right? So we want to know something about that. That's going to take us to our y equation. And again, I'm going to write this in the same exact way. It's the velocity of the plane relative to the ground, but just pick the y component out. That's the velocity of the plane relative to the wind. Pick the y component out plus velocity of the wind relative to the ground, y component. All right, so let's go through this. The plane's velocity relative to the ground. It's only pointing in the y direction, right? We knew that from the outset. So if I have a vector that just points along some direction, okay, that component is the magnitude of the vector. Does that make sense? So if I have a vector, 3 I hat, right? Okay, the x component is 3. But the magnitude is also 3, because that's all there is to the vector. There are no other components. So I can write the magnitude of vector VPG, which is what we want to know, equals these two things added together, which will now work out. Okay. Velocity of the plane relative to the wind in the y direction. Well, I have the magnitude, which is 400 miles per hour. And if I multiply that by sine of my angle theta, which we talked about over here, and which we just discovered, is 96.22 degrees, measured off the x-axis in the standard way. That would be this y component. Do we agree? And then, if I added to that the y component of the wind velocity, that would be 50 miles per hour, sine of 30 degrees. So can someone crunch that for me? Because this will actually give us the answer we want.
$422.6.
Yeah, I would agree. So 422.6 miles per hour. So we're actually getting kind of an assist from the wind here. You see that? With no wind, we'd be traveling at 400 miles per hour. But because the wind is kind of at our backs, pushing us forward a little bit, we do gain a little bit of extra velocity. Okay? So any questions on how this one works? All right, I think we have like less than 10 minutes left, so realistically not enough time to go through another one. But again, if you have lab today, we're going to be going through review problems. Okay, so we'll see more examples like this. That's it though.